right, so I've drawn some cute little pictures here with light poles just so that we can kind of visualize and see what's happening. Okay, so we got a light pole. The light clearly is shining here. Here's a person standing, and this would be the shadow. All right, as you walk towards a light pole, the length of your shadow gets smaller or it shrinks. Okay, as you walk towards a light pole, thus dx dt, this is if I let this be x, the change in x over time, dx dt, the change in x over time would be negative, indicating that it's shrinking because it's getting smaller. Okay, so that's what this notation is, dx over dt, the change in x with respect to time. Okay, now let's say we got the same thing. We got a light pole, we got a light here, we got a person, he's going away from the light pole. Again, here's his shadow, and we're letting that be denoted by x. As you walk away from the light pole, the length of your shadow gets longer or it lengthens. All right, thus dx dt, the change in the length of the shadow with respect to time would be positive to indicate that it's getting bigger or it's growing. It's getting longer. Okay, this, you don't have to necessarily write this down, because if you print it out, if you print them out of the notes, it's nice, cool little pictures if you want them in your notes. Okay, you can write it down, but you don't have to. Okay, so now stated another way, this is helpful for some AP questions. All right, and basically it's just stated again here. Now look at my picture, the way I've done this here, trying to show you that, okay, so here's a person, the light beam's coming down here would be the length of the shadow, but if the same person was over here, the light beam would show here, and look how longer it is longer. See, the farther away from the light source you get, that shadow gets longer. Okay, and even when I drew it out, I mean, I didn't draw this to scale or anything, but I created this on the computer, and I mean, it just naturally, the angle at which that beam comes creates a longer line here than it does here. Does that make sense to everybody? It is a very tall light pole. Yes, I did not draw to scale, but when you create things on a computer, you just do what you can. All right, so a couple points. Your shadow shrinks as you walk towards the light pole, which we just talked about. Your shadow grows as you walk away from a light source. Okay, so two important concepts you got to remember. All right, now it is important to recognize that the speed of the tip of the shadow, the speed of just the tip of the shadow, does not depend on the distance of the man from the pole. The speed of that tip, because obviously if he's moving, the tip of that shadow is going to move, right? And the speed at which that tip of the shadow does not depend on how far he is from the light pole. Okay. And so what they'll do is, in some of the questions, they're going to give you extra information. They're going to try to trick you, and you're going to think that that changes, and it doesn't change. All right. In other words, the speed of the tip of the shadow is constant at the rate at which the man walks away from the pole, regardless of how far he is from the pole. So I just stated it in another ways. The speed of the tip of the shadow is constant at the rate at which the man walks away from the pole. Okay. So you will forget that, and you'll come across the problem, and then you won't even realize it's happening. And then as soon as I say something to you, you're going to go, oh, yeah, I remember that now. Okay. All right. So like I said, this handout is on the website. You can download this if you want to keep it. All right. So that it's something that you can reference on a regular basis. Okay. So let me put that up, and then let's take a look at some problems. Okay, now unfortunately we're going to actually have to write the problems out because I did not Xerox anything. With you doing the first half of this lesson at home independently yesterday, you know, then you don't have a handout for it. So we're going to have to write the questions down. All right, so let's go ahead and date it. Today is the 15th. So October 15th. We're doing some more related rates. And even though day one was on your own, we're still on technically day two. We've covered this stuff. All right, so let's look at an example here. Let's say a man who is 6 feet tall, is walking at a rate of 5 feet per second toward a light pole. That is 20 feet high. At what rate is the length of his shadow changing? So the key here is going to definitely be in reading carefully, highlighting important pieces and parts of the story problem. Okay, so the man is 6 feet tall and he is walking at a rate of 5 feet per second toward. Okay, so he is walking at a rate of 5 feet per second toward the light pole or toward the light source. Okay, so that's going to tell you how to set up your picture. All right, and then at what rate, so we're clearly trying to find a rate, is the length of his shadow changing. The length of his shadow changing. So that's going to tell you like what you're trying to find. Okay, so we need to set up a picture here. Okay, so I'm going to have a light pole, for lack of a better source here. I'm not going to draw very good. Okay, 20 feet, right? The light pole is 20 feet tall. We have a guy and he is walking toward the light source. So here's our guy. And he is walking toward the light pole. So I indicate that he's walking toward the light pole every time. All right, now we know this is going to be a right triangle, right? So I'm going to go ahead and draw my right triangle out like this. Here would be the light source coming down. I will extend it there a little bit. All right, so here's his shadow, right? Now, he is 6 feet. I didn't add that in there. Let's put that right there. Not a good place to put it, but he's 6 feet tall because it told us that. Now it says he is walking at a rate of 5 feet per second towards the light pole. Okay. If he is walking at a rate of 5 feet per second, that's the change with respect to time. I'm going to let that be X just because I got to be doing X something. But that's going to be from here to here, right? Because he's walking towards this. So from here to here, we're going to say is X. I got to pick something. And they've given me the rate of change. So they have given me the rate of change of X with respect to time as being 5 feet per second. Now, he's going towards the light source. So is this positive or negative? Negative because it's getting shorter, right? So negative 5 feet per second. So that was really my given information right there. I didn't write given. Let's put that on there. I didn't give myself enough room. We were given that. I had to choose where I was going to put it on my diagram. Okay, now I want to find, what do I want to find? I want to find the rate. At what rate is the length of his shadow changing? So this distance here would be the length of the shadow. So I need to come up with another variable. So I'm going to say the length of the shadow can be, I don't know why. We just need another variable in there. And I want to find a rate. So I want a rate with respect to time. So I'm trying to find then, if I called this y, what am I trying to find? I'm trying to find dy over dt, dy over dt. So are we good so far? I'll let you ponder that a minute. Okay, now what I'm hoping that you can see is, not that I want to clutter this picture up, but I got to clutter this picture up. Okay, think geometry, think a long time ago. I got a triangle here, right? Which I know 6 and y. All right, do I also have this triangle? Yep. So what are those similar triangles? And I know this side and I know this side. And I of the little yellow one, I know this side and I know this side. Can I not write a proportion? So see, your geometric equation is not a formula. You are going to write a proportion. Okay, you're going to write a proportion. So the quote formula you're going to use is going to be a proportion. So it's not really a formula like it was yesterday, like the area of a circle or the volume of a cone, but it's going to be a proportion. Okay, so I'm going to take my little yellow triangle and I'm going to do what? Y over 6. And then I'm going to set that equal to, now, what side of the pink triangle corresponds to the Y side of the yellow one? Not XY, but X plus Y, because if I take this distance plus this distance, I would get that whole distance across the bottom. So X plus Y over what corresponds to the 6 side? The 20 side. Okay, so far so good? All right, now what we're going to do is I'm going to write this proportion over here, like Y over 6 equals X plus Y over 20. All right, now, just to make things a little bit easier, I'm trying to find dy dt, right? The length there, y, with respect to time. So, yeah, if we cross multiply and solve for y, and then get a y equals something, then when I take the derivative, it's going to be so much easier. Okay, so that's what I want you to do. I want you to solve for y. So I'm going to put solve for y. It just makes it a little bit easier. So 6x plus 6y equals 20y. I want y on the left-hand side. Okay, so negative 14y over a negative 6x divided by 14. It's going to be positive, so y is going to be equal to 6 over 14. 3/7. Did you have to necessarily do that? But I don't want to take the derivative of this yucky thing. Cross multiply down, solve for y. Makes now I can real easily take the derivative of that with respect to time. Okay, so here's my little equation that I'm going to manipulate. I'm going to now do implicit differentiation. Take the derivative with respect to time. So when I take the derivative with respect to time, my y turns into a dy over dt. Taking the derivative of that 3/7 x is just 3/7. Remember the chain, dx dt. Because implicit differentiation requires that chain. Okay, so the derivative of y, which I didn't say, is 1, and then the chain, dy over dt. The derivative of 3/7 x is 3/7, and then put the chain in, dx dt. Okay, so then there's my derivative. Okay, so let's box that in because that's important. I will check that, obviously. Okay, now I've got the derivative. So on all related rates, once you get to your derivative, you plug in what you know and you solve for what you need to find. So we were given dx dt. Okay, so dy over dt is equal to 3/7. Plug in the dx dt, which is negative 5 feet per second. Multiply. So negative 15 over 7 feet per second. Now let's stop and think about this. I'm going to write a therefore statement, but let's stop and think about this. I'm wanting the rate at which the length of his shadow is changing. If he is walking toward the light pole, is the shadow growing or shrinking? And it's a negative, so that's good because it should be shrinking. Okay. All right, now let's attempt to write a therefore statement. You would not need the negative, correct. All right, so I might say when the man is walking toward a light pole, I'm going to do LP for light pole at 5 feet per second. Yes, you need to put that in there because that's important, the speed at which he's walking towards. The length of his shadow. And let's do the other one. Since I know it's shrinking, if I want to say is shrinking, then I'm going to put the positive value in. If I just want to say the length of his shadow is changing at a rate of, I would do the exact answer I had. Okay, so the length of his shadow is shrinking at a rate of 15/7 feet per second. It takes almost as long to write the therefore statement as it does to work out the problem. The key to this is drawing an accurate picture, making sure everything is labeled, and then writing a proportion that's going to work. And you really have to pay attention to the phrase, because this one asked for the length of his shadow. Sometimes it's going to ask for the rate at which the tip of the shadow is moving. They're just going to change up what the question is asking for. Josiah, I thought you had a question coming, maybe?
No.
It shouldn't concern you. I mean, some things that look complicated when you first look at it really isn't that complicated once you grasp the concept of what's going on. Related rates by no means are going to be the worst things that we do this year. By no means will this be the worst. Probably solving differential equations is going to be probably the hardest thing, I think. Differential equations. First of all, you don't even know what a differential equation is yet. But yeah, I would probably say out of all the stuff we do, that's probably the hardest. Say what?
The dread I feel with that.
Well, it'll be a long time away. We got a lot of learning to do before then. All right, so let's try one where we're actually doing the tip of the shadow. Okay, let's do one where we're doing the tip of the shadow. Okay, so let's see. All right, a man. We're going to stick with the same man and the same light pole for the most part. All right, a man who is 6 feet tall. That's just because I lack creativity in my story problems. Is walking at a rate of 5 feet per second. He walks the same speed all the time. We're going again toward a light pole, LP, so we can shorten a little bit here. That is 20 feet high. Okay, so same setup for our story problem here. At what rate is the tip of the shadow changing? Okay. I'm going to highlight at what rate is the tip of the shadow changing. Now, even though it's the same setup, I still got a 20-foot light pole. I still got a 5 foot or 6 foot man. All right. The picture and the way we label the diagram is not going to be the same because they've asked for something different. Okay. So actually, let's really focus on this. I'm going to maybe make this a little bit bigger than I did before. There's my light pole at 20 feet. Okay. Here's my guy, and he's 6 feet. Okay. Now, obviously, we know we've got proportion here going with two triangles, two similar triangles. Okay. So we know this is our setup. Again, this is the dude's shadow, right? So we'll put the shadow in there. Now, before I do anything else, at what rate is the tip of the shadow changing? Okay, here's the tip of the shadow, right? And he's walking toward, let's put that on there. He's walking toward the light pole. Okay, so it's still asking for a rate. It's still asking for a rate, but it's a rate of the tip of the shadow. Now, so how can I get you to think this? I'm not concerned with this distance. What distance am I concerned with? If I want to know the rate at which the tip is changing, say it again. My had your mask on, I can't see.
It's not changing, is it?
Well, it's going to be because he's going to be walking this way. The shadow's going to be changing, but that tip will be moving this way.
You're not concerned with this distance, you're concerned with this distance.
Right. So you said, I'm not concerned with this distance, I'm concerned with this. So what were you pointing
The
to?
hypotenuse of the triangle instead of the, or not I forgot the word, but you're concerned with the z side instead of the x or y side.
No, but close, because I don't have anything, I have no information about this hypotenuse.
The triangle should be changing, isn't it?
The triangle is, well, not the triangle. If I want the rate at which this tip is changing, watch my fingers. So what's this tip? If he's walking towards, the tip of the shadow is going to go this way, all the way up to the light pole. So if I have a question that asks for the rate of which the tip of the shadow is changing, this distance right here, I could label whatever I want, x, y, whatever, let's call it y. And then the tip, the rate at which this is changing is dy dt. The rate at which the tip changes is in relationship to the base of that light pole, because as he walks towards it, that tip moves closer and closer. And once he gets to the light pole, it's going to be like right there, right? It's that full distance for his tip, the tip of the shadow. Okay. All right. So if I let that be y, because we focused on the question first, then I'm trying to find the rate that distance is changing, which is the dy over dt. So I'm trying to find dy over dt. All right, now let's put the information on that was given to us. He was walking at a rate of 5 feet. All right, so he's walking at a rate of 5 feet per second. So that's this distance in here. So from here to here, yeah, I don't care. We can call it x. You can call them anything you want. Okay, so there's my x. And so then I was given that rate as dx dt. And that's, again, since he's going towards the light pole, negative 5 feet per second. Now, I still have my two similar triangles. I've got this triangle, and then I've got the big triangle. Okay, but I'm missing this distance in here. Because I need, if I'm going to write a proportion, I need 6 over something.
X plus y over 20 is going to be y minus x.
Yeah, this missing distance in there that you've got to calculate on your own there is going to be y minus x. So that distance is y minus x. So yes, I should be able to then write my proportion or my formula or whatever you want to call it. It's a proportion, but we could call it the same thing that we've been calling it, and the other ones will say it's a formula. All right, so we said y minus x over 6. And then big triangle, corresponding side would be y over 20. And so there again, when you get to that formula part right there, then it's a proportion. If you don't get that right, you're kind of screwed the rest of the way down. Now, again, I'm setting this up on purpose so that whatever I'm trying to find is y or dy dt. All right, you don't have to do that. You could change up your variables or whatever. But then when I write my proportion of y minus x over 6 equals y over 20, then I can say, okay, if I'm trying to find dy dt, I want to solve for y. If you set your variables up in a different way and you were labeled things differently and you were trying to find dx dt, you would solve for x. Okay, so cross multiplying down, 6y, 20y minus 20x. And then move that 20 over. I'm going to have a negative 14y equals a negative 20x. Solving for y, I'm going to have a positive. Y equals 20 over 7, or 20 over 14 would be 10 over 7. But let me screw up. Okay, so so I guess what I'm saying is I don't want you to memorize, oh, I'm always supposed to solve for y. No, you're not. If you define the variables differently, you're not going to solve for y. You're going to solve for whatever you set your find up for. So if you choose to label these things differently, it's not going to always be set a solve for y. All right, once you get to that equation, it's a nice little equation, then now you can take the derivative with respect to time, or in other words, your implicit differentiation. So when I do y, derivative of y is just 1, and then with the chain, dy dt. Derivative of 10/7 x is just going to be 10/7. And then you got to remember the chain, dx dt. So setting it up and doing it this way just makes it really nice because then you just plug in -5 feet per second. So 10/7 times your -5 feet per second. So was that -50/7? So -50/7 and then feet per second. Okay, now here again, stop and think about what we did. This tip is moving toward the light source to the left. So does it make sense that it's negative? Okay, because it's getting that rate is getting smaller. It's getting because you're going towards the light pole to the left. Okay, so then you write your therefore statement. And again, like I said, that therefore statement sometimes takes longer than writing out the problem. On this one, I would say when a man is walking toward a light pole, again, I'm going to use LP at 5 feet per second. And then you need to really specify the tip of his shadow is, and again, you could say any way you wanted. Here, let's try is moving toward the light pole at a rate of, okay, so the way I phrase the sentence, do I need a negative value or do I need the positive value?
No.
Need the positive, so 50/7 feet per second. So like I said, you guys will write your own individual therefore statements. Just make sure that it corresponds to what's actually happening in the story problem. Make sure that you pull out information of at what point in time are we talking about. Okay. At what point in time are we talking about? At what's happening? Be very detailed in that therefore statement, because on the ACP exam, they like the really good therefore statements. Okay. Justification, just since we've been talking about the ACP, you would probably get a point for writing a picture. You would probably get points for the given and find, which I'm going to give you a point for a correct picture. I'm going to give you a point for writing your given. I'm going to give you a point for writing your find. I will then check the proportion here. I will check for whatever you solve for based on what your information is on your paper. I will then check this derivative to make sure that derivative is correct, and then here, and then the therefore statement. So, I mean, there's lots of points that are going to add up over time on these. All right, so